welcome everybody. Our speaker today is Jerome Wettstein, who is from the ETH in Zurich, and he will talk about properties of half-harmonic gradient flow. Thank you very much for coming, and please go ahead.
Yes, thank you very much for the introduction. As Armin said, I will be talking briefly about some properties of the half-harmonic gradient flow, some results I obtained this year regarding existence, uniqueness, and regularity of solutions, which have decreasing energy in time. As a short summary of what I'm going to do, first I will recall some notions from harmonic maps. These results are quite standard and most of you will know these by heart anyways. It's just to draw the analogies to the fractional case and recall some of the main techniques that might appear later on as well. Afterwards, we will discuss fractional harmonic maps. How are they defined? What kind of regularity applies? And then finally start talking about fractional gradient flows by again first discussing the harmonic gradient flow as a basis and expanding in an analogous manner to the half-harmonic gradient flow. In the third part, I will discuss my main result, what is new about it, what has been known before, and finally I will give some of the ideas of the proof, especially regarding uniqueness, which is probably the most interesting part of the work. Okay, and then let's start immediately with the first part with a brief excursion into harmonic map theory. Just to fix some notation throughout the talk, whenever I'm referring to H1 or H1 half of some manifold, some other manifold, I mean these are the maps defined on M with values almost everywhere in N, so quite standard notation. And in this way, we define a weakly harmonic map as a map in such a space, H1 on M with values in N, which is critical with respect to variations in the same space with respect to the Dirichlet energy presented here, where we use a Riemannian metric on M as well as a Riemannian metric on N. Usually we assume N to be an embedded submanifold of Rn. Therefore, with the induced standard metric, which we can do by Nash's embedding theorem, so these, the gamma ij's simplify and become the delta symbols. And throughout some parts of the talk, we will also assume that M is a subset of R2 with the standard metric as well, so the entire energy simplifies significantly. Additionally, we will mostly restrict to the spherical case anyways, where all these simplifications apply quite well. Okay, I mean, as I said before, if we assume these simplifications, the energy becomes much simpler in a quite standard form, and the Euler-Lagrange equation can be computed by using variations of energies involving the closest point projection. The general result is that in a distributional sense, the Euler-Lagrange equation tells us that minus the Laplace-Beltrami operator of U actually is orthogonal to the tangent space of N at the position U itself. This becomes naturally particularly simple in the case that N is the sphere, since the normal space of the sphere at any given point U is just the linear space spanned by the vector U itself. So by testing against U, we find that in the case of a spherical target manifold, this is the Euler-Lagrange equation we're interested in. A particularly interesting thing to note, which is easy to see, if we assume U is in H1, then the gradient of U squared is just in L1. So this is a critical kind of equation since we may not directly apply Calderon-Sigmund theory due to the right-hand side being an L1 function. Okay, so since regularity in a really direct manner fails, the question is how can we get better regularity for these kinds of maps? And especially in the two-dimensional case, which I'm going to be mostly interested due to the analogy to the one-dimensional fractional case. This relies on several different authors' contribution, for example, Berthuel, Coron, Eller, and Rivieres, and basically answers the question of regularity positively by using compensation phenomena tied to Wente-type estimates. An interesting feature of the harmonic map equation is that actually, if we know that the weakly harmonic map is Holder continuous, we may iterate this kind of regularity and obtain smoothness. So the entire question really boils down to skipping or bridging the gap between weak solution and Holder continuous solution. And this gap can be taken by either using moving frames, as introduced by Hélin first, or by the gauge techniques inspired by Uhlenbeck's Coulomb gauge, as Rivieres used them later on in 2007. The interesting thing about Rivieres techniques is that it also answers the question of conformally invariant energies and its critical points regarding regularity positively, which was a conjecture, I think, by Hildebrandt. In any case, in both techniques, the key ingredient is that we reformulate the equation in such a way that special linear combinations, so-called 2D Jacobians, appear, which have better regularity properties than we would a priori expect. And this is really the content of this result that I'm now showing on this slide. It is a theorem by Venti, and later on it was generalized by Koifman, Lyon, Meyer, Sems, with applications to diff curl quantities or higher dimensional determinants and various different formulations. In the two-dimensional case, the theorem we're mostly interested in is the one displayed here. Namely, we are given A and B in H1 of the ball, U in W1P with 0 boundary values on the same ball, P being strictly smaller than 2, and we assume it solves this equation here. A priori, the right-hand side is only in L1, but due to the special structure and some compensation going on in here, we may deduce, well, U is actually continuous. The gradient is in L21, a Lorentz space, which is slightly better than just being in L2. And the second order derivatives actually are in L1, which we could not deduce straightforwardly from the Calderon-Sigmund theory. And all these norms can naturally be bounded by the L2 norm of the gradient of A times the L2 norm of the gradient of B. This is quite well known and forms the basis of all regularity considerations regarding harmonic maps. So a question is, how can we now get actually better regularity? We will briefly just go over the spherical case, just to recall how the main ideas go. And in this scenario, actually, an observation by Shatta was that the Euler-Lagrange equation is in fact equivalent to a system of conservation laws. The conservation laws being given by the equation here. So the divergence of ui gradient uj minus uj gradient ui being 0. Now these terms, or at least the first part, ui gradient uj, also appear in the harmonic map equation. So if we add and subtract the same term as we do in here, we actually see, okay, we obtain that minus the Laplacian of uj is equal to this sum here, where we sum over the i's, which now involves, and in some sense, the product by an antisymmetric matrix with divergence-free components, plus some remainder term. But we observe that by summing over ui, we have the scalar product of ui as well as some of its directional derivatives. And since ui takes values into in the sphere, u itself will be orthogonal to its derivatives. Therefore, this part here actually vanishes, and all we're left with is the product of the matrix with the gradient of u. So this shows us that that Venti's result can be applied in this scenario, and actually by iterating this kind of argument in small balls, we could actually obtain a Mori decrease, which then leads to higher Hölder regularity and therefore smoothness. The observation by Rivieres, especially in his 2007 paper, where he applied the gauge techniques, was that the key property is not the divergence freeness, but the antisymmetry, which links the equation to gauge transformation, since the antisymmetric matrices are part of the Lie algebra of rotations. So this has a very geometric meaning to it. Yes, so, and this was already all about harmonic maps. So now we're ready to discuss the fractional harmonic case, which is in some sense quite similar. For this first part on fractional harmonic maps, we will usually allow both the domains R and S1, since the theory does not really need to distinguish both of them. We can just use stereographic projections in order to switch between the two whenever we want. And the main definition, as it was introduced by Dalio and Rivieres in 2010, regarding half-harmonic maps, is that a map is actually half-harmonic with values in some target manifold n, if and only if it lies in H1/2, and it is critical for the following energy functional as given here. So 1/2, the integral over the domain of minus 1/4 Laplacian u squared integrated. Again, naturally, with respect to variations in the same space. The very easiest example one could think of for such maps would be if we take just n to be the real line, which leads us to the Euler-Lagrange equation minus 1/2 Laplacian of u being 0. And for example, if we take S1 as the domain, the only solutions are the constant maps. So we see that there is some regularity going on in this simple example, and we expect something similar to hold in general. As for harmonic maps, we may discuss the Euler-Lagrange equation and find something very similar to the local case. Namely, the Euler-Lagrange equation is nothing but stating that in a distributional sense, minus the 1/2 Laplacian of u is actually, again, orthogonal to the tangent space of n at u, which is really the very same statement as we've seen before, just replacing the Laplacian by the 1/2 Laplacian. The most natural formulation to restate the Euler-Lagrange equation in a way that reminds us of the harmonic map equation would occur in the case that n is a sphere. In this case, we can write the equation in the following manner, namely the Euler-Lagrange equation is equivalent to stating that minus the 1/2 Laplacian of u is equal to u times the half gradient of u squared, where the half gradient of u is defined by the following quantity, which depends now on x and y. And in order to just get a function depending on x again, we have to integrate out the dependence of y in the square of the 1/2 gradient. These notions of fractional gradients and fractional divergence also were introduced by Mazowiecka and Chikora in 2018 and have proven to be very useful in order to make the connection between harmonic maps and half-harmonic maps, or even more general n over p harmonic maps, more close and render the arguments and proofs more similar than they were even before. Okay, so why should one care about half-harmonic maps? Firstly, these maps are connected to free boundary minimal disks. This was observed, for example, by Dalio, Martinazzi, and Rivieres, but also by Milo and Sire and Dalio and Picatti. And they are closely connected to singular limits of Ginzburg-Landau equations, which is again seen in the paper by Milo and Sire from 2015. Naturally, since the fractional harmonic map equation bears such similarity to the harmonic map equation and the structure of the variational definition is quite similar, a natural question to ask is whether or not these solutions are regular or just break down at some point. And regularity actually has been investigated immediately by the authors defining it at first, Dalio and Rivieres in 2010, showing regularity in the case of the target manifold being a sphere and later in general. 2 years later, Armin then showed that for n over 2 harmonic maps on n-dimensional domains, the same holds true. In the spherical case, he proved with Dalio together that for n over p harmonic maps, the same holds true a few years later. And in the recent paper from 2018, Armin and Mazowiecka showed that we can even draw the connection more closely by using the notions we've seen before here with the half gradient and the half divergence. Okay, so regularity has been studied, solutions are regular, and the main ideas go pretty much along the same lines as in the local case, meaning you apply localized versions of the of either fractional Venti type inequalities or so-called free commutator estimates, which are special linear combination of terms, which just like in the Venti estimate case have better integrability properties than each of the summands on its own. A simple example is like the fractional Leibniz rule, in which each individual term has pretty bad integrability, but having the special combination, you have some compensation going on, which allows you to deduce more than you would be a priori. The key idea is then just apply the localized estimates, take care of the behavior far away, which introduces some tail estimates, which are usually not dangerous, therefore allows you to establish again a Murray decrease, and by some Adams type embedding, you obtain finally that it is Hölder continuous. And again, this can be iterated to smoothness. Yeah, and again, here summarized the different points of view taken by the authors. Dolio and Rivieres in 2010 applied the free commutator estimates, which are again related to some kind of Leibniz rule compensation, while Mazowiecka and Sikora really closed the connection between harmonic and fractional harmonic case by introducing a fractional Novelty type inequality. And this result is one that I would like to briefly show to you and discuss a bit, because we will need it later on in the uniqueness of the half-harmonic gradient flow case. And the main statement of the result is, as you see here, you're given S a regularity exponent between 0 and 1, P strictly between 1 and infinity, and we assume we are given F an LP function on R2N with respect to the measure indicated here. We assume it has vanishing S divergence. Now, vanishing S divergence does mean that F paired with any kind of S gradient vanishes. And S gradients were defined in complete analogy to the 1/2 gradient we've seen before. So in some sense, this just means that F vanishes on the subset of S gradients. And moreover, besides the LP function F with vanishing S divergence, we also assume G to be a function in WSQ, Q being the dual Hölder exponent of P. And then we have that the product of F with the S gradient of G is actually in the Hardy space, which is quite similar to the observation by Koifman, Leo, Mayer, Sems, which also introduced Hardy spaces as better integrability, therefore allows us to have better estimates. And naturally, an estimate holds in terms of the LP norm of F and the LQ norm of the S gradient of G. And the latter one, the SG LQ norm, can also be related to the WSQ norm by some general results on Triboli-Zurkin and Bezov spaces. So this is really the main connection one has to draw. And then we can discuss regularity for fractional harmonic case, for fractional harmonic maps, really analogous to the harmonic map case. Namely, we again restrict ourselves to the spherical case. We observe, similar to Shata's observation in the local case, we have a system of 1/2 conservation laws, which really is the same as in the harmonic case, just replacing gradients by half gradients and divergence by half divergences. And these allow us now to do the same kind of simplification, introducing an anti-symmetric 1/2 divergence-free matrix omega times the 1/2 gradient of U, plus now some remainder term. The remainder term is due to the fact that, in contrast to the real gradient that is tangential to your manifold at every single point, the 1/2 gradient does not need to be. But the remainder has actually better integrability properties simply due to the fact that it describes basically the behavior of 2 points which are in the manifold. And as we get closer and closer, these will behave like x minus y to the power 2. Since the idea is that if you consider ux minus uy, the first order expansion would involve the differential at ux of u, the differential of u at x, which would be again tangential to your manifold and therefore would vanish in the summation. So you only have the second order term. So you have better integrability properties leading to better estimates, and therefore the term tu is not dangerous. So in some sense we can again ignore this part and only have this equation which we really have to estimate. And here again we can now use the fractional Novelty type inequality, or indeed a localized version of it, in order to deduce a Mori decrease and therefore Hölder continuity. So this really shows you that both cases are, while quite different in the sense that one is local, one is non-local, the techniques involved are quite reminiscent of one another. So, and then let us conclude this brief excursion into fractional harmonic map theory by just mentioning 2 more results. Namely, these maps have also been studied with respect to bubbling by Francesca Dalio in 2015 for the target spaces being spheres and general targets, showing that there occurs bubbling at the most finitely many points. Outside of those, converges nicely. So what one would expect from these kinds of bubbling sequences. This is based on some concentration estimates in neck regions, and outside of them, there's no energy concentration, so everything behaves quite finely. Okay, so now we're finally over with the introduction and may turn to the gradient flow part of this talk. And indeed, before I enter the gradient flows, in the specific case of harmonic gradient flows and half-harmonic gradient flows, I would like to briefly recall what a general gradient flow looks like. In general, this is a function. We are given, for example, an energy function on a Hilbert space H with values in some R. We assume it is sufficiently differentiable in some sense, for example, Fresher differentiable. And the corresponding gradient flow is then just defined as the steepest descent parabolic equation, meaning that in time, we always go into the direction of steepest descent in the hope that we will reach some local or even global minimizers of our energy functional, which would then also provide stationary points of the energy function, and therefore solutions to the associated Euler-Lagrange equation. Naturally, gradient flows are quite ubiquitous in mathematics and studied in many different incarnations. For example, there's the mean curvature flow, the Ricci flow, Wilmer flows, and for our case, the most interesting one, the harmonic map flow, since it is quite similar to the half-harmonic map flow I will be discussing later. Since we can turn from studying a elliptic PD to a parabolic one usually has good regularity properties, so it is also quite nice working this way, and it helps us approximate solutions. And we could connect these also in some sense to homotopy questions or more theoretic approaches such as Floer homology, which in some sense counts the flow lines between two critical points, which are in this case periodic orbits of Hamiltonian vector fields. Okay, now after having this general introduction, we would like to discuss some of the theory associated with the harmonic map flow, which is again governed by an equation such as this, which does not really, in this form, does not really look satisfyingly at all. So a more natural way to write it down, at least in the spherical case, would be in this way. We have that the partial t derivative of u minus the Laplacian of u is equal u times gradient u squared on some time interval 0 to t times omega, the set where you would like to study the entire equation. And since we consider the equation on some omega, which is a smooth subset of R2, we also have to include boundary conditions on the boundary of omega as well as at time t0. And we assume at time t0 we are some h1 function, and on the boundary of omega we always are smooth. These kinds of gradient flows have first been studied by Els and Sampson in 1964, at least in the non-positive sectional curvature case for the target manifold N, leading to existence results. And later on in 1985, Struve proved a systematic existence and regularity result for arbitrary target spaces, which now relies on estimates which consider the concentration of energy around certain points in order to take care of bubbling, as well as the energy, and introduces estimates which are stable under approximation, therefore leading to existence results for general boundary data from the case of smooth boundary data. Also in this result, he proves uniqueness in a certain class of function, but unfortunately, this class of function does not cover the case of weak solutions, but only strong solutions. Strong solutions meaning that he considers functions for which we can make pointwise sense of the differential operators applied to the functions, or in the LP sense at least. This minor point of contempt was later resolved in 1993 and 1995 by Rivieres and Frère by completely different means. Rivieres dealt with the small energy case with values in the sphere by some kind of absorption trick, which allowed him to deduce that solutions which are weak are actually also solutions such as Struve found them, and therefore may apply the uniqueness result from Struve. Frère, on the other hand side, used moving frames in the spirit of Hélin in order to deduce again better regularity such that Struve's uniqueness result applies. So there is a different kind of technique, but the main idea behind it, how we could get uniqueness, is the same. Okay, so after having discussed the history of these kinds of flows, the main result that was proven by Struve in 85 is the following. If we are given omega sufficiently nice with good boundary, U0 initial data in H1 with values in Sn -1, smooth boundary data for all times on the boundary of omega, then there exists a unique solution with non-increasing energy in the class given here, meaning that we are twice differentiable in the space direction, once in time direction. And actually this solution will be smooth everywhere except in finitely many points where the energy concentrates and therefore leads to the bubbling off of an harmonic map. The number of bubbling off points can actually be bounded, since whenever a harmonic map bubbles off, it must concentrate a certain amount of energy in order to be non-constant, which can be bounded from below. Therefore, we get an estimate such as this here, which tells us that we can really only have finitely many bubbling off points, and we can put this into relation to the initial energy, since we cannot lose more energy than we initially had. Okay, so let me just quickly mention the uniqueness in the result by Struve does not deal with weak solutions, but rather with solutions in this set of functions, meaning that we can split the time interval into finitely many pieces. And on each of those, we have that the space derivative, it is twice differentiable weakly in the space direction, and these belong to L2 over the time interval times omega. So we can make sense of the equation on each of these time intervals in an L2 sense. So it is only a strong solution. For weak solutions, which would only allow for H1 regularity in space direction, one has to do a bit more, and this was done by Rivieres and Frère later on. Okay, as I said before, existence and regularity are dealt with by establishing uniform estimates depending on concentration estimates and energy bounds by Struve, which shows that if we have existence and good estimates for smooth solutions, we also obtain the same kind of estimates for bad boundary data, or H1 boundary data at least. Therefore, we have all good results in this case, and the kind of uniqueness that Struve established is just obtained by considering two different solutions, checking what kind of equation the difference solves, and testing this equation against the difference itself. This immediately leads to the fact that u minus v must be 0 in the L2 norm, therefore they must be the same for all times by iterating over finitely over small time intervals until you reach the first point where it should differ, and then concluding by contradiction. Okay, moreover, Struve includes the possibility of bubbling occurring at finitely many points, but he did not have an example ready for finite time bubbling. This was later established by Cheng in 1992. He proved that there may be bubbling in finite time by constructing subsolutions which force a growth of the gradient in order to ensure that we have a bubbling off of a sphere at one point in finite time. Further results in this direction were obtained by Topping, who discussed so-called reverse bubbling, as well as obtained asymptotic estimates for the convergence as t goes to infinity. 2 weeks ago in this seminar, I think Yun-Cheng Wei also talked about his research on the inner-outer gluing scheme and its applications, especially also to the harmonic gradient flow. And he talked about the different types of bubbling, like bubbling off in finite time, reverse bubbling, where you add in some sense a bubble and increase the energy, and a third type of bubbling that could occur. So what's important is really that keeping these kinds of bubbling in mind, the non-increasing energy really forces that, for example, no reverse bubbling can occur. Therefore, otherwise uniqueness would be violated. So non-increasing energy is a key assumption to ensure uniqueness. Okay, and finally, again, Rivieres and Frère proved the weak uniqueness by their different kinds of approaches. And we will now discuss briefly how Rivieres did it, since his approach is the one we will also encounter in the half-harmonic gradient flow for uniqueness. And the key idea he had was that he could prove a result such as this one here displayed, which was part of his PhD thesis in 1993. Namely, if we assume u to be an H1 function, which solves basically the harmonic map equation with values in Sn minus 1 up to an L2 perturbation, which for our situation will mostly be minus the time derivative of u at a fixed time t, with then actually u would be as integrable as we could hope for and as regular as we could hope for, namely u is in H2. The way one applies this then in order to establish that a weak solution is actually a strong solution is we consider finitely almost every time t where such an equation holds, we integrate it, obtain good estimates of the H2 norm of u. We also, by applying the Ladish-Senskaya type estimate to the L4 norm of the gradient, we can get a second term on the right-hand side, which also involves the H2 norm and some energy, which we can bound by the initial energy. And if it is sufficiently small, therefore we can absorb it. And thus we would obtain, in some sense, a good bound for fixed times t, which we may then integrate over time. I will elaborate on this later, just to kind of draw the picture here. In the half-harmonic case, we will take care of this in more details. Instead, we can also discuss the fractional Ladish-Senskaya estimate and its application. For now here, we will just briefly go through the proof, see how it works. And the first main step is one can Shatas identities we have previously discussed apply in the case of the harmonic map equation, but we could apply them in a generalized manner and employ some sort of Hodge decomposition in order to rewrite the equation we have above in the way presented here, including now the bracket u, gradient u, gradient b part, which is a sum of 2D Jacobians, a part which is gradient phi times gradient u, where phi is in H2. So this part here is actually in LP for any p strictly smaller than 2, b being in H1, and f still as introduced before. So we rewrite the equation slightly by Shatas trick as before, adding and subtracting this, the same part, and we're left with this. In order to further simplify, we now even eliminate the boundary values gamma by introducing a w, which is smooth with the right boundary data, and define v to be u minus w. Then the equation solved by v is minus Laplacian times the same kind of operators here, and we absorb all terms that appear from w into f tilde, leading to f tilde still being in L2, since w is a C infinity function. Therefore, in particular, its gradient is, for example, bounded. So we're now left with this kind of equation. The next observation is, okay, we could now also absorb the part gradient phi, gradient u, by allowing f tilde to just be in LP for p strictly smaller 2, leading to, after inversion of the Laplacian, the following identity. Now, this does not look like we have gained much, if anything at all, but actually this allows us to deduce that v is in W14 by a very smart trick. Namely, what we do is we split b into a regular and a small part, small in the L2 norm sense. This can be done by usual approximation techniques and allows us then to rewrite the equation in this way. We subtract the part with gradient b hat, which is small, and put it on the left-hand side. Now on the right-hand side, we fix v. So here it is no longer, in some sense, a variable. It is a fixed function, which is in L2. And we take L2 two-dimensional Jacobians with the gradient of b tilde, which is smooth. Therefore, these gradients are bounded. These gradients are in L2. So the entire thing here will be an L2 function, and therefore the sum will be an LP function for any p strictly smaller 2, since f tilde is in this space. So after applying the inverse Laplacian, we obtain something which is in W1Q for any q strictly smaller plus infinity. The key idea now is, okay, we can consider the left-hand side as an operator from W1Q to itself and check whether or not this operator is invertible. If it is invertible, we have for any given q strictly bigger than 2 and exactly one solution. And this one solution must agree with the solution in the case Q equals 2, which would be our initial V, meaning that the unique solution, which exists, for example, in W14, would again be V, implying that V has actually W14 regularity, which would be sufficient to conclude that U is in H2. And this is now done by observing, okay, we have for the operator on the left-hand side, just the identity operator, plus some perturbation. And the perturbation actually leads to a small perturbation by virtue of applying Sobolev embeddings, leading to, okay, we can bound the W-1P norm of this expression by the L2P over P plus 2 norm, which by Hölder's inequality can be bounded by this expression. Here, this part is very small since we constructed gradient B hat this way. So in the case P is strictly bigger than 2, this is a small perturbation, therefore the inversion argument applies. In the case P equals to 2, the embedding theorem does not this argument does no longer work. But we have a replacement, namely the Venti type estimate, which also tells us, okay, for the 2D Jacobians, we have H-1 regularity. And if we recall the statement, this can be bounded by the L2 norms of the gradient of B hat and gradient of V. Again, here, having a very small quantity, allowing for this part to be a small perturbation, not affecting the invertibility. So indeed, if this is small, the left-hand side is invertible. The right-hand side, we have fixed V, meaning that we have something in W1Q for any Q strictly smaller plus infinity. As a result, we deduce V is in W14. Since U is just V plus W, a smooth term plus a W14 term, it is again in W14. Therefore, the gradient of U squared is in L2, and thus minus Laplacian of U is in L2, and finally U is in H2. And this is the argument behind this step. So now having done this proof, we will slowly go over to the half-harmonic gradient flow in order to then finally apply these kinds of techniques in the half-harmonic setting and see how these translate. The goal in the half-harmonic case is, again, we would like to establish some result analogous to the harmonic gradient flow, meaning we would like to have existence, we would like to have regularity, we would also like to have some kind of uniqueness, especially in the weak setting, and maybe some bubbling procedures. The main equation is again governing this process is again given by the steepest descent equation, which can be rephrased by knowing what we have talked about before. This equation here, meaning the time derivative of U plus minus the 1/2 Laplacian of U is equal to U times gradient U, 1/2 gradient of U to the power 2. A first thing that one might wonder is, what do we actually know about these types of equation? In 2017, Armin, Yannick Sire, and Wang did prove that weak solutions for the fractional harmonic gradient flow do exist, at least associated to the energy functional given here for some subset of Rn, at least if we consider the maps taking values in homogeneous manifolds N. The restriction to homogeneous manifolds is due to the techniques used, namely they apply some discretization argument and minimization on each of the subparts. And thus, in order to pass to the limit, they need some symmetry of the target manifold. So in the case of the sphere, for example, they already had existence, but the techniques I'm going to apply also generalize to arbitrary target spaces, even if they don't have any symmetry at all. More further results concern the bubbling procedure. For example, Sire, Wei, and Cheng proved in 2017 by the inner-outer gluing scheme that was talked about, for example, 2 weeks ago in this seminar as well, that bubbling at time t equals infinity can occur, and actually there can split off arbitrarily many bubbles, at least in the case that the target space is S1. And they conjectured in the same paper that no bubbling in finite time would be possible, but this is still an open problem. And if solved, and for example, if this were true, the result I'm going to show you that I was able to prove would actually imply global existence for any energy, since no bubbling could occur. Okay. Before now finally stating my main result, I just want to mention a peculiarity. Since in the case of the sphere, we have a very nice formulation of the half-harmonic gradient flow, it is natural to wonder, do we also have such a nice or well-suited formulation as well? And the answer is no. Indeed, we have several different kinds of formulations which are suited for different parts of the process of proving the result I'm going to show to you later. For example, we could formulate the half-harmonic map equation for general manifolds in the way presented here. The intuition behind this is that we have the identity matrix minus the differential of the projection map, the closest point projection, which would be the orthogonal projection to the normal space of the manifold at the point U. So what this really tells you is, okay, the gradient flow does really satisfy the required equality, meaning the orthogonality to the tangent space. This is particularly useful since the right-hand side here is closely connected to a commutator, which allows us to obtain higher regularity and actually allows us also to employ some parabolic maximum principles, which we shall encounter later on, therefore is quite well suited to prove existence of solutions, at least locally. While for the uniqueness part of the results, there are other types of formulations better suited, for example, this one below, where we involve quite a few half gradients and some divergence part, which does not look that great, is equivalent to the formulation I presented to you above, and is quite well suited to prove strong uniqueness. There are also various other formulations which sometimes resemble more a second fundamental form type formulation, but have some disadvantages of their own. So there is not a unique best choice to be done. Okay, so we're finally at the point where I can show you my main result. This is what I've discovered in the spherical case, namely, if we are given an initial datum in H1/2 on S1 with values in the sphere, and we assume that for a sufficiently small epsilon, it has smaller energy then there exists actually a unique energy class solution, which is smooth everywhere, satisfies the boundary data in an appropriate sense, has non-increasing energy. And in fact, for appropriate sequences of times going to infinity, we can also deduce weak convergence in H1/2 and strong convergence in L2 to a point. The last statement being a rather simple exercise based on the fact that if it would bubble off at times infinity, it would need to have some amount of energy in order to ensure that it is a non-constant harmonic map. But since we assume small energy to begin with, we can just take epsilon small that such a bubbling cannot occur. Okay, so what is the novelty of this result? As we've seen before by the result by Armin, Zira, and Wang, I think, existence for homogeneous target spaces has been known, but what we now got is general existence for arbitrary targets. And we also got a uniqueness result, which was previously unavailable due to the techniques involved. Moreover, the kind of proof that I'm giving for the result here also works for arbitrary target manifolds in quite the same way. So we, not only for arbitrary target manifolds, but also for arbitrary energies, under the caveat that we assume that we restrict ourselves just to a small time window. So we get global existence if we have small energy and existence on a small time interval with arbitrary energy. So you have a kind of trade-off, since in the large energy case, you could have bubbling at finite time. Okay. Again, the existence and regularity result is based on good estimates, quite similar to, in a similar spirit to Struve's result by approximations, and based on existence results for good boundary data, and regularity is then obtained by a bootstrap procedure, which is rather straightforward, but quite technical, and the result in my paper deals with this entirely, but I'm gonna skip it for this talk. The uniqueness statement is based on naturally Rivieres trick. This is why I discussed it in this detail before. And for this, for the remainder of the talk, we will as I said before, not discuss regularity or the convergence, the latter one being a simple exercise and the former one being too technical to show here, since it does not provide any insight into the problem itself. Okay, so let us turn to the discussion of uniqueness. Uniqueness of strong solutions in the sense as also Struve showed it in 1985 for the harmonic gradient flow is again obtained by taking two different solutions, considering their difference, check which equation they solve, test against the difference itself, showing the L2 norm must vanish everywhere, therefore it is they are the same. So there's nothing really interesting about this part. The most interesting part about it maybe is the application of a fractional type Lodich-Shenskaya type estimate, which is quite well known nowadays too. So this is not too special as well. But what is really interesting and has not been done before in this setting is the application of Rivieres trick. So we will talk about this. And mainly we will talk about the lemma that Rivieres had in the case of the harmonic gradient flow or the perturbed harmonic gradient flow, which in the fractional world reads like this. We have again the half harmonic gradient flow plus the perturbation. And we then show, okay, it will have maximum regularity, the most regularity we could expect from such an equation. Now, I promised to you earlier that I'm going to tell you how we could use this result in order to establish actually that the solution of the weak harmonic gradient flow does belong to the class where Struve's result applies, and also the strong uniqueness that we could prove in the case of the half harmonic gradient flow. And the argument for this is basically we use a characterization by Pretz and his collaborators telling us that, okay, the L2 norm of the 1/2 gradient squared is actually equivalent to the L4 norm of the 1/4 Laplacian of u to the power 4. And this one here, now by Lodich-Shenskaya's fractional estimate, can be bounded by this product. Okay, this is quite nice, but we don't know how to apply this yet. Now we consider the equation we are given. This was minus the 1/2 Laplacian of u is equal to u times the 1/2 gradient of u squared minus the time derivative of u at a fixed time. We consider this for all fixed times t where this equation applies, and then by applying by considering the h1 norm of ut, which can be estimated by the 1/2 Laplacian of u actually, we obtain such an estimate due to the right-hand side that we have previously discussed. The one term here being due to the L2 norm of u itself. Now, we observe that here, the term emerges as we've discussed before. Therefore, we can estimate this by the quantity given by the fractional Lodich-Shenskaya estimate, leading us to this expression. And the nice thing here is now, okay, we have the h1 norm of ut as well as an energy quantity at a given time t. We know that the energy will be decreasing since we only consider weak solutions with decreasing energy. So naturally, this can be bounded by the energy at t equals 0, so by minus 1/4 Laplacian of u, the L2 norm. And by absorbing this part to the right-hand side, we're left with something like this. This part here can be bounded by the initial energy at t equals 0. And if this was sufficiently small, we can assume that this entire thing, the entire factor here, is actually bigger or equal than 1/2. So by some constant, which could be put on the other hand side, therefore showing that the h1 norm at a fixed time t of u would be bounded by some constant plus the L2 norm with respect to the on the circle of the partial derivative in time direction. Integrating now this with respect to time leads us to the conclusion, okay, u will be in h1 of any finite length time interval times s1. So we are in the case where the strong solution result applies. Therefore, we can deduce, okay, even weak solutions satisfy the uniqueness property. So we will not dwell too much on the proof of the lemma, since the talk is already going quite long. It is basically quite similar to what Rivieres did in the local case. in some sense, we have to substitute the application of a Hodge decomposition, but this is not too troublesome. And the Venti type estimate will naturally be replaced by the fractional Venti type estimate by Armin and Mazowiecka. And this leads us finally to observing again that we find such a structure. Again, we have a remainder, which is not dangerous at all. We have an L2 function. We have here a divergence-free matrix. We can approximate this by a smooth and a small part, both of which are divergence-free by introducing some additional functions, putting the small part to the right-hand side, inverting the 1/2 Laplacian, and arguing precisely as in the harmonic case. We then may conclude that, okay, for any p bigger or equal than 2, we actually may know that U already belongs to the triple Isokine space of 1/2 regularity and the integrability exponents P2, especially in the case P equals to 4. This again leads us to the W1/2 4 regularity, which would be required in order to make this equation imply that the 1/2 gradient of U is in L2. So this is now more of a technical exercise. Okay, so to conclude the talk, I will just very briefly address the existence part. Regularity will not be talked about that much. To deduce the existence part, again, we argue as in the harmonic gradient flow case. So we argue by approximation. Therefore, the entire argument is based on the existence of solutions for good or smooth boundary data. The remainder of the argument, meaning establishing good estimates and everything, proceeds similar to what Struve did, but one has to take care of the non-locality of the problem, which is at some points troublesome and at some points not so much. So really, what is the most interesting part is establishing existence, at least for small times. And to establish existence, the key ingredient is, okay, we know that to have a solution, we would like to have this operator vanish on some time interval. In order to have this vanish on some time interval, we apply a local inversion type theorem. Namely, if we have U a smooth function, and we can show that the differential of H at U is invertible, then the image would contain a neighborhood of H of U as well. Now, a neighborhood of H of U would also contain a modification of H of U on a small time interval, for example, from 0 to epsilon to be 0. Since if we let epsilon tend to 0, this converges into LP norm to HU as well. So we could at least obtain for a small amount of time a solution. Naturally, this idea of applying local inversion theorem then leads us to investigating the differential of H, which can be expressed in this way by direct computation. And we observe that the first part here is actually an elliptic invertible operator due to the boundary values we need to introduce to make sense of the argument, plus some part which involves only H, therefore this is a lower order term, and a part that only involves the 1/2 gradient of H, again a lower order term. And we know that lower order terms therefore must be compact operators, which lead us to the conclusion, okay, this is an invertible operator plus some compact operator, thus it is a Fredholm operator of index 0. This again allows us to conclude, okay, invertibility would be equivalent to injectivity, thus it suffices to consider elements of the kernel of the differential. And actually, elements of the kernel can be shown by a bootstrap argument to be smooth, and if they are smooth, we may also talk about the equation solved by the gradient of U squared. Just very briefly, if one computes this, this shows us that we obtain some estimate like this, which by a parabolic maximum principle shows us, okay, the maximum must be obtained at time 0, where it must vanish due to the setup of our operator H. So H must be 0 everywhere, therefore the kernel will be trivial, since by assumption H was a generic element of the kernel. So the local inversion theorem applies. A nice thing about this argument is that quite the same argument also shows us, okay, if H of U is 0 on some small time interval, it will be smooth there, and by some application of the parabolic maximum principle, it will take values in the right manifold. So this also gives us more than just the vanishing of H. this kind of argument applies in a more general setting here. Okay, so now I'm going to conclude the talk by just mentioning a few further directions one could pursue here. Naturally, what I did, I only discussed the spherical case. Everything applies to general manifolds in the very same setting. We could also deduce, as I said before, local existence, at least for a small time window, if we sacrifice the small energy assumption. But as long as we have small energies, we can also show, okay, it exists globally. And in the large energy scale case, we also don't have uniqueness of weak solutions, only of strong ones. So this is another drawback. A question that is open is the conjecture by Zero, Wei, and Cheng on the finite time bubbling, because if the conjecture was true and there would not be finite time bubbling, the result I showed you would already imply global smooth existence. But it is open and one would have to consider this in more detail and to resolve it. This is not an easy question. Finally, also naturally, the uniqueness of general weak solutions is an interesting problem to study. And since the moving frames method seems not to generalize this easily, this would require some additional work. So, and with that, I arrived at the end of my talk. Thank you very much for your attention, and I'm sorry for going over time.
Thank you very much. Now the questions, remarks, comments.